Hello, class. I didn't start lectures till a little bit late today because I well, actually I have no idea why I didn't do it. um but we're starting a new area of the class. And in fact, really statics, and you might have realized this as we were moving through statics. And this is how it is for mechanical engineering, the same way that it was for you in electrical engineering, right? You get network theory 1 first, then you get network theory 2 after that, then you get analog devices, then you get, all of those various different things, and the semiconductor devices, all of those things. And so it's a step process. The same thing is true in mechanical engineering, and the two fundamental courses really in mechanical engineering are statics and dynamics. And so we've really gone through a lot of statics, and a lot of the stuff that we learned in statics, just like network theory 1 and network theory 2, are going to be standalone fundamental courses for you as you go through your electrical engineering curricula. That's what these are, statics and dynamics for mechanical engineers. And what I want to get into in the dynamics portion now of this, and we've covered a lot of things. We now know what vectors are. We know what force vectors are, acceleration vectors. We know operations of vectors. So we know a lot of things that we don't have to redo again. And in fact, really what I'm going to do today is this should be, in many ways, a review, because when we talk about kinematics, we're talking about the equations of motion, right? Or that's what you were originally told that you were learning when you were in physics class in high school. That's I assume. And so what I want to do is I'm going to go through a review of some of the things that we've already done. And in fact, I'm going to go back and just sort of flip through what it would be an actual dynamics. Yes, I taught dynamics at Purdue, so so it shouldn't be too much of a problem. I have degrees in both mechanical and electrical. And so anyway, the first thing that I want to do is we've gone through all of the systems of units and all of that. I want to look at just a very simple problem. That's just an equation of motion problem. In fact, this equation of motion, I want to put down two things. Equations of motion, of course, we know what those are. We have three equations of motion. And I'm gonna write this too. We have three power equations, don't we? Power equals VI. That's right, that's three equations. That's P equals VI. And then if we were to merge that, of course, with V equals IR, we would get three power equations. We get P equals I squared R, we get P equals V squared over R. But are there really three power equations? No, there's one power equation, P equals VI, right? V equals IR, that's Ohm's law. We made it with that, we come up with three. And so what we say is we have three equations. With the equations of motion, in many ways, we're saying the same things when we teach this to high school students. And the first thing that we would say is, okay, well, we have final distance equals original distance plus original velocity times time plus 1/2 acceleration times time squared, right? We know that as the equation of motion. Or we were probably taught that as the equation of motion when we were in high school. We also have another equation of motion that says that the final velocity is going to be equal to the original velocity plus the acceleration, if it's constant acceleration, times time, right? So that's another equation of motion. And then we have a third equation of motion let me flip through here. This really isn't what I would call an equation of motion. It's just the other equations of motion that are all put together. And so we say that this is an equation of motion too, and that would be, God, have I got enough room here? V final equals the square root, I'm actually going to use the radical sign, of V original squared plus 2 times the acceleration times S. Now, I'm going to say that S equals S sub F minus S sub 0, because S sub 0 usually is 0 anyway, right? So that's just my qualifier there for the third equation of motion. And you're probably saying to me, oh, I don't remember that equation of motion. Yeah, V final equals V original squared plus 2 times the acceleration times the distance covered, and all taken to the square root. And that's the third equation of motion. It certainly makes it easier to work with things, you know, when you're just working with this. T is no longer, right? T is a variable in both of those two equations. So what we've done is we've actually solved those equations relative to one another, and then we've come up with an equation that gives me my final velocity without time involved at all. But we do have time implied in the distance that it goes, because you know, that's the distance equation. I'll see how I go today. I did you know, a few lectures yesterday, so but I have some tea. Now, how did I get here, take these two equations and come up with this equation? I'm going to actually do that derivation for you. All right. And in doing so, I'm going to use an identity. Let's go up to this equation right here, because I'm just, you know, so let's solve this equation for t. If I was to solve that equation for t, because I'm going to use it in the other equation of motion, that would be V final minus V original, right? I'm just taking that off this side, throwing it back over there, and then I'm dividing by A. Does everyone see what I did there? All right, not a problem. Then it becomes a little more complicated. What I'm going to do is I'm going to take this equation of motion, I'm going to substitute that in for t, just to show you, you know, what's going on and how we're going to get there. And it's always a good thing to see. I like to you know, point it out. So let's say that that is the first step. I'm just going to draw a thing there. I think I can fit it in here. So S final equals S original plus V0, and then what is T now? T is V sub F minus V sub O over A, right? I've just substituted this into that. So we could say that this is part 1, and we could say that this is part 2, substituting T. Yeah, you see, that's where classes are so good, because you get a break. You can ask students to answer questions or whatever. But we're going to get through this. Oh my goodness, I just realized I forgot to set the timer. Just a second. Okay, I have an idea. We've been going about 10 minutes. So let me just set the timer. I'll start it there. Say we've been going 7 minutes. I have no idea really of time. But anyway, let's get back to this substitution into our equation. So we've then got plus. Now I've got 1/2, right? So 1 divided by 2. Just a second, I think someone's knocking. No, I'm sorry about that. Nobody was knocking. All right, let's get back to this. So let's substitute that 1/2 A, and then time squared. So the same thing, V sub F minus V sub 0 divided by A, and then all of that squared. All right. And you can see that this really, that's going to be, anyway, so let's go on to part 3. So if I do that and expand this out, I'm just going to go S sub f minus S sub 0, because why not get that over to that side? And then that can really be, you know, S like I have there. And then let's expand out the other side. So I'm going to get V sub 0, V sub f over A minus V sub 0 squared over A plus 1 over, now let's see what I've got here. I've got that squared, so that's going to be A squared, and that's got A in the top. So A and A squared, that'll cancel out one of those A's, and that'll just make it 1 over 2A. Does everybody see that? And then what I want to do is expand out the numerator. So I've got V sub f squared, and then minus 2 V sub f V sub o, and then plus V sub o squared, right? Everyone see how that all worked out there? You know, if I were to expand this out, this would give me, let's just, I hate to write all of this out all over again, but I think I'm going to have to. V sub o, V sub f over a. Where have I seen that before? Well, why don't I just expand the whole thing out? Minus V sub o squared over a plus, now if I've got, well, V sub f squared over 2a minus V sub f V sub o over a. See how the 2's canceled out? The 2 canceled out there, so I just did that. I just left that O there. And then plus V sub o squared over 2a. All right. So why don't we make all of these 2a? All right, so we have everything over 2a, and we can get rid of 2a on the other side. So if I do that, I'm going to have to make the denominator and the numerator. Denominator, that's a minus. Numerator, that's fine. Minus, I should have left some room here, right? 2, 2. Okay, so we've got 2 all the way across there. So S sub f minus S sub o. Boy, I sure hope this. I've got this all written down here. I've already done it, of course. But now, why don't we multiply this by the 2a, right? Because we've got 2a all the way across there. So I've got 2 V sub o V sub f minus 2 V sub o squared plus V sub f squared, right? Because I got rid of the 2a, minus 2 V sub o V sub f, right? Plus V sub o squared. Does everybody see what's happening here? So I've got this canceling out with this. I've got minus 2 V sub o squared, but I've got plus V sub o squared. So that really becomes V sub f squared. I won't go too fast. And then that minus, of course, wipes that out. Minus V sub o squared, right? So let's take that V sub o squared over to the other side. Let's see, 3, I don't know, 4, 5. If this is step 4, then I guess that's step 5, and then this is step 6, which is the finale. Take that over to the other side, and I've got V sub o squared plus 2 times A times S sub F minus S sub O, which of course that's what S is, right? And then if I take that to the square root, that gives me my final. And so I've just basically taken these two, just like we've got P equals I squared R and P equals V squared over R. I've taken these two equations here and put them together so that I could come up with this equation here that doesn't have T in it at all and gives you a final velocity, and also, you know, some other things that you could find there too without T. And so that is the first part of our, I hope I started that. Yes, I did. All right, that's the first part of our kinematics. And I want to go on and look, though, at another aspect of kinematics too, and I've left some space there to point this out. You know, we can do an analysis of the velocities and everything, or we can look at it as energy. So we know that kinetic energy is going to be 1/2 mv squared, right? And we know that potential energy is mgh, at least at the surface of the Earth, that's what it is. You know, let me just check and make sure my video settings haven't changed or anything. No, looks pretty good. Okay. Yeah, okay. Is that focus? Yeah, no, that's the right focus. All right. Not the right brightness sometimes. Sometimes when I put my hand here, it brightens up, that's for sure. I don't know why. But as far as the focus goes, I've got the focus pretty good, I think. Now, let's go on, because we've got that equation, we've got those equations. What I want to do is I want to look at a couple examples, just, you know, easy examples, but dealing with both rectilinear kinematics as well as curvilinear kinematics, which we're going to look at in a little while too. I thought I would do just an interesting little problem, right? Let's say that you go to a water slide park. So I've got a little example here. You go to a water slide park and they've got the new super duper high super slide that you're going to go down. And you're climbing up there and you're saying, well, this is really high, so I better put my son down at first. Now your son, I say weighs, but I really mean that his mass is 20 kilograms. I do that just because, you know, we actually talk about our mass in kilograms. If you're European or Australian or Japanese or whatever, you know, in the metric system, you talk about your weight in kilograms, but in fact, it's not a weight, it's a mass. And when we talk about our weight, it actually is a weight because we use pounds, and pounds are a unit of force, not a unit of mass, right? This child would weigh 20 kilograms on the moon, or would have a mass of 20 kilograms on the moon and have a mass of 20 kilograms on Earth. Whereas, you know, his weight would be 1/6 of what it is on the moon that it is on Earth in pounds. Anyway, so I just thought that I'd point that out. We're at the water slide park, and they've got a new water slide that is 20 meters high. Now, you got to remember that a meter is a little more than 3 feet, right? So this is about 60 feet high. And here's what the water slide looks like. The water slide looks like this. You start off and it's, well, let's not say it's purely vertical, but it's sort of vertical. And then at the bottom, you come into a pool type area where you slide into this pool and it slows you down and, you know, drags your swimsuit into the wedgie position, I'm sure. So now, what is the potential energy that we have when we're standing up there 20 meters above this, about to put your child, a 20 kilogram child, inside here? And then how fast will your child be going when he hits the thing down in the bottom? Assuming that, air friction, we're not going to get up to speed so high that air friction is really going to play a significant role in your child going down here. Okay, let's we'll draw. There's your child. Let's see, we got to write help. And then there's you. Okay, off you go, Sandy. Down you go. So you've got a mass of 20 kilograms. I try to add levity and humor to these lectures. It's not easy. I mean, we're talking about dynamics. So his potential energy is going to be mgh, right? So we've got, don't have enough real room. Well, I'm going to have to do it. So 20 kilograms times 9.81 meters per second squared times 20 meters. So the potential energy that the child has going down the particle, you can think of it like a particle or whatever. I'm calling it it's a storybook problem, so I'll call it a child. But it's something that's, or a 20 kilogram package, whatever you want, sliding down a chute at Amazon. Basically the same concept. What I'm doing, though, is I'm using energy principles. Could I use the same? Could I use my equation of motion? Sure. Yeah. But I can use energy principles, and I think that that would be faster in this case, right? So my potential energy then, 20 kilograms times 20 meters times 9.81 meters per second squared is 3,924 what? What would those be? It's a unit of energy, isn't it? So we know that it would be joules. So 3,924 joules. That's the amount of energy that potential energy I've got when I'm standing at the top of the, or my child has when they're standing at the top of this slide about to go down. It's 20 meters high. Yep, so they've got water. There's no friction whatsoever. Let's totally cut out any friction on the slide due to the water going down the slide. And in fact, you're going down just about as fast as the water is going down the slide. I'm assuming, right? So we know that's the case, and then we know that that has to equal 1/2 mv squared. So let's just figure this out. That means that my velocity, can I do this all in one substitution? Let me just see. 2 times 3924, right? So 2 times 3924 joules. Always put your units down there. And then that's going to be divided by m, which is 20 kilograms. And which would be because we multiplied it by m, right? And then we have to take that to the square root, don't we? So if we do that, V equals 2 times 3924 divided by 20, all taken to the square root. That gives me a velocity of 19.8. I already written down, but I thought I'd do it again anyway. Meters per second. Right? So that's what my final velocity is coming off the end of that slide. I shouldn't say well, it would be my final velocity too, right? Because it shouldn't make any difference what the mass is because the mass was put in and the mass was taken out, right? So if we have If we have PE equals KE, I've got 1/2 mv squared equals mgh. Immediately, everybody can see the m falls out of there. So it doesn't matter if it was me. And in fact, this whole part of the information that I gave you here, as far as determining the final velocity, wasn't necessary, because I will go down there and I will come off at the same speed that my child is. Now you're saying 19.8 meters per second. Is that fast? 19.8 meters per second. Is that fast? Is that like a jet fighter speed, or is that, how fast is 19.8 meters per second? Well, we know that there are 1609 meters in 1 mile. I want you to memorize these things. 1609, don't use 1600, use 1609. Be the engineer, right? Okay. 1609, and then how about seconds? Well, we want to get rid of seconds and put hours in there, don't we? Right? So that would be our conversion factor. And I think everybody can see that that's about 2.25, isn't it? 2.25, 3,600 divided by 1609. Let's see, 3,600 divided by 1609 is 2.237. 2.237. That's the conversion factor from meters per second to miles per hour. Times 19.8 meters per second. So we're going 44.3 miles per hour. Me and my child are going pretty darn fast when we're coming off the end of that slide, aren't we? Yes. I hope there's a pool at the end of that slide. 44.3. Of course, we're up there 65 feet, aren't we? 65 feet in the air and zooming down here. The truth is that the water that flows down here is actually slower, and it's slowing you down a bit when you're going down that slide too. Even though it's really high, the water is tending to slow you down unless you're skimming above the water, and then that is a problem. You know, there's another conversion factor that I want to look at here. You know, this being the conversion factor for meters per second to miles per hour. So I think anybody, you know, that figured out that 728 miles per hour, right, is the speed of sound. Mach 1. M1. 728 miles per hour. So, you know, think of this conversion here. Remember that this is actually don't remember these two things, 1609 and 3,600. Boy, that's the easy part. And then there you go. You've got miles per hour or meters per second, which are the two things that you'll work in for most of your life. Now, let's move on, because I want to change RPM. What is RPM? RPM is revolutions per minute. Now you're going to be doing a lot of things that deal with RPM, revolutions per minute. And in fact, even in this dynamics course, we're going to be working with revolutions per minute. When you get into motors and controls, you're going to be working with revolutions per minute. And you're going to want to turn that into radians per second, because engineers cannot use revolutions. They can't use degrees. They can't use revolutions. They've got to use radians. That's the only engineering unit that we can use. So how do I get rid of revolutions? Well, it's one revolution, right? One revolution equals 2 pi radians, right? Let's get rid of minutes. 1 minute equals 60 seconds. right? So you can see what I've got here. I don't know, let's put some real revolutions per minute in there. Well, let's one. Yeah, I should have put like something in there, but and let's do 1,000. I'll get my no, I'll just do that. Look, that even looks like 1,000. Here, I'm gonna take my red pen. I'm gonna separate out those two things. There you go. Let me just. There we go. I don't know where I'm going to write the 1,000, but let's do that. 1,000 revolutions per minute times 2 pi radians divided by 60. So you're thinking it's probably around 104.675, something like that. I haven't done it yet, but I'm thinking that that's about what it is, because it's got to be, isn't that like 6.28? So that's like 6. That's like 60. So it's got to be divided by 10. So I'm assuming it's going to be around 110, 104, something like that. 1,000. Oops, wait. Turned it off. 1,000 times 2 times pi. I want to get this exact. Divided by 60 equals 104.72. 104.7 radians per second, right? So 1,000, oops, don't do that, Scott. There we go. Yeah, sometimes I do talk to myself more and more during the COVID crisis. So yeah, 1,000 revolutions per minute times 2 pi radians per revolution, right? Because isn't that what it is? It's if we look at the unit circle, isn't it 2 pi? Isn't that where we start? We start at 0, and then we go up to pi, and then we, excuse me, pi over 2, then we go to pi, then we go to 3 pi over 2, then we go to 2 pi, right? In the unit circle. So we're going around 2 pi radians, 1 revolution. I know I'm probably, you're probably saying, oh God, we did this back in grade school, back when we learned about the metric system. No, I'm sure that for some of you, a lot of what I'm talking about is, new. Always remember the unit circle, no matter what engineering you're in or what you're doing, the unit circle, and remembering that this is your cosine axis and this is your sine axis makes it so easy. Plus the complex numbers, remember those. And the complex plane, you'll be working in that. You'll be working with complex algebra, complex variables in grad school if you go to grad school. So, do all of those. So I wanted to bring those couple things up. How we're switching from different things, some conversion factors, because we're just getting into this. So I'm trying to cover the things, but we've really already covered vectors and stuff like that. I'm just trying to cover the kinematics first before I get into the really interesting stuff, which is the kinetics. That's right. Not kinematics, it's kinetics. Now, I'm going to do an example problem. I've got a black hole, right? There you go, black hole. And I've got a block of meteoric iron. In fact, this meteoric iron is really steel. Such a hard steel. It's been hardened by going around this horrible black hole and everything else. But it's got a super eccentric orbit where it takes it right next to the black hole and then as far out as it can go, and then all the way right next to the black hole again. We're assuming that the radiation coming out of the black hole is not blasting into this. So, going around, And what I want to find out, what we know the gravitational attraction of the black hole, and we can say that it would be constant over as an average over the entire trip of this steel meteorite, is that it takes 10 seconds for it to complete its journey from its apogee to its perigee, right? That point right there, furthest away, is called an apogee. You're learning something in the apogee. And this place right here, the closest that the orbiting satellite or spaceship or whatever gets to the body it's orbiting around, is called its perigee. All right. So for it to get there, it takes 10 seconds. And we know that the gravitational constant, I'm going to slice a piece of this off, for this black hole is going to be 10,000 meters per second squared. 10,000 meters per second squared. Whoa! Let's put that up here. So G is going to be 10,000. That's 1,000 times, right, as great as the gravitational constant attraction of the Earth. All right. How much more would that be a gravitational attraction than, let's say, the sun? What's the sun's gravitational attraction? At the surface of the sun, if we can actually call the top of the boiling molten, plasma that is the surface of the sun, when we see the sun, we see a circle, right? So at the surface of the sun, the gravitational attraction is about 276 meters per second squared. 276 meters per second squared. So, it's not that great compared to this black hole that I've got that's got a 10,000 meters per second squared. So we want to find out a lot about this, right? We know it takes 10 seconds. We know that the velocity out here, right, just going toward the black hole, is going to be equal to 0 meters per second, right? Because it's going all the way out. In fact, we're just really looking at it in this one dimension. So it comes zooming down, and then it comes zooming back, right? So it's going down, and it's coming back over and over and over again until it's finally going to hit another steel piece and crash into the black hole or whatever it's going to do. All right, so that's what it's doing, going around in this big, huge circle, and we know that it takes 10 seconds for it to go this distance here. We know that during those 10 seconds, it's constantly accelerating at 10,000 meters per second squared. So right at its perigee, how fast is it going as it passes by the black hole? That's what I want to know. How fast is it going? Well, the final velocity that it goes, assuming that the original velocity up here, it's like throwing a baseball up. When the baseball gets to the top, it's not going in the vertical direction anymore, is it? So its vertical direction velocity is 0, right? Throwing a ball up in the air, comes up, and then its vertical velocity, so Vy equals 0, right? If I was doing that with the baseball, of course, in this direction, I could say that too. Now, I'm doing the same thing. I'm throwing this huge, boulder up here, and it's coming back down. So I have my original velocity, which is 0 meters per second, plus my acceleration, 10,000 meters per second squared, right? Times my time of 10 seconds. So I've got a final velocity right when I get closest to the black hole of 100,000 meters per second. 100,000 meters per second. How fast is that in miles per hour? Oh my God. We've got it right up here, don't we? And we know that this equals 2.237. Remember when we committed that to memory? 2.237. That's the last two numbers, by the way. So you can see why I rounded it to 7, 2.23742. But you don't have to really remember that conversion factor. You've got to remember that it's 1609 meters in a mile. It's 3,600 seconds. You don't even have to remember that. You can just figure that out, right? So that's what it is. So that's what my final velocity, right near that thing is going to be. We're going to be screaming past there, 223,000, and that's 10 seconds. So we're going to go from 0 to 223,000 miles per hour in 10 seconds. How about that? Talk about acceleration. You know, how far is that distance? How far is that distance, that 1/4 distance that we're going to be covering there, right? How far is that? Well, the distance we cover is the original distance. We'll say that's 0, right? Wherever it is, 0 meters plus 0 meters per second times time. I'll make 10 seconds. I'll do that one. 0, right? Plus 1/2 times the acceleration, 10,000 meters per second squared, times 10 seconds squared. You know, I should separate that out so that everybody knows that that is that, right? This equation is up here. That equation is down there. I guess. I don't know. We'll say it is. So yeah, all I've got to do then is figure out what that is. And of course, 10 seconds, that's a second. 10 seconds squared is 100. 100 times 10 is 1,000. 1,000 times 1,000 is 1,000,000. So 1,000,000 divided by 2 is 500,000 meters. Remember, it's meters, not kilometers. So that's only 500 kilometers. So this asteroid or whatever is actually is accelerating in a 500 kilometer distance. It's going from 0 miles per hour to 223,000 miles per hour. That fast, right? And of course, think of if it's got a g of 10,000 meters per second squared, the acceleration is so much greater than it would be. Now, I've still got other examples and stuff that I want to do, but my alarm went off, and I think that I've already probably recorded too much with the derivation and everything else. So I'm going to hold this first lecture there because I didn't have my timer on exactly, but I think, you know, and it's a good place to stop too, because I've got a couple more examples we're going to go into that are a little more complex. All right.